Hello and welcome to the beginning of Chapter 7. So this is our new unit on systems of linear equations. And systems of linear equations just means dealing with more than one linear equation at a time. So a system just means more than one. So the first section in this unit is called developing systems of linear equations, because what we're going to do is talk about how we can actually come up with some equations on our own, using some real life scenarios or translating kind of word problems style of scenarios. So here's the first scenario that I have, and it's just a really simple spinning game. So you've probably seen spinners and board games and things like that before. And so this spinner has 6 sections on it, and you can either get 3 points or 2 points. So 3 points, 2 points, 3 points, 2 points, 3 points, 2 points. And so we're going to go ahead and spin this and see what happens and how many points are we going to get. So the first time it lands on 3 points. So I'm going to go ahead and check off that we got 3 points. Go ahead and click it again. 3 points again. Oh, I just wrote on it. Okay, here we go. Spinning it again. 3 points again. Oh my goodness, this thing is rigged. Three points again. Two points. My goodness, it's starting to get worried. I thought this thing was broken. 3 points. Three points. Three points. Whoa, went a little bit crazy. 2 points. And final spin, 2 points. All right, so there were your scores. So in total, your spinner, or our spinner, landed on the 2 points 3 times. And it landed on the 3 points 7 times. We did 10 spins total. So to represent the total score would be T, the total, is equal to, well, 3 times, or 2A plus 3B, I should say. So 2 points for every time we got result A, and 3 points for every time we got result B. And then if we go ahead and calculate that, we got result A 3 times and result B 7 times. So our total score would be 6 plus 21, which is 28. So a pretty nice score there. Okay, so moving down. Now imagine that you had a partner, and let's say that they did the same thing that you just did and spun the spinner 10 times. I'm not going to spin it 10 more times. I'm just going to show their results here. So here's their results. Oops. 1, 2, 3, 4, 5. So they actually got each one 5 times. Okay, so then theirs would be T equals, again, 2A plus 3B. So 2 points for every time they got result A, and 3 points for every time they got result B, and they happen to get each of those 5 times. So their score would be 25. Okay, so what I'm trying to illustrate here is that you can come up with equations from something as simple as keeping score in a game where somebody either scored 2 points or 3 points. And on here you can see the A's and B's, and I maybe should have written them on here as well, but we said that A was the 2 point column and B was a 3-point column. So another time that we come up with our own equations is often when we're working with word problems. And so I found that this is something that it's an area where some people struggle, especially if they're still learning English and kind of working on those terms. So I'm going to try to explain this as clearly as I can. How we translate from English into mathematics. It's kind of like going from one language to another. So in some ways, if you speak multiple languages, you already know a bit about the concept of translation, which is great. So in English, if we say that there are 20 more small buses than large buses, well, the first thing we need to do is assign variables. So the small buses we're going to call an S, and the large buses we're going to call L. And there's 20 more small than large. So the amount of small buses is 20 more than the large. So seeing a word like more means that we're thinking of adding. Okay, if we say that the length, we're going to call that L, is 2 feet longer than the width, which we call W. So the length, the word is an equal sign. So the length is 2 feet longer means plus, and then W for width. So here the length is means equals 3 meters shorter than the width. So that actually means shorter than is going to be a -3 than the width. So we're actually going to switch these around because we don't like to say -3 plus W. So we'll say that the length is the width -3. So that one is tricky because it's not just as simple as saying minus sign. A lot of people think that means 3 minus W, which is wrong. It's actually W minus 3, shorter than the width. So if you take the width and take off 3, that gives you the length. So two numbers differ by 5. Differ means that if you subtract them, the result is 5. So your two numbers could be like X and Y, and they differ by 5. So that means that X minus Y equals 5, or you could have said Y minus X equals 5. Either one of those would have been okay. Two numbers have a sum of 7. Sum is the result of adding. So if our numbers again are X and Y, you could say X plus Y equals 7. If we take in some cans and bottles for refunds and we get 5 cents per can and 10 cents per bottle, we're going to say that cans are C and bottles are B. And so we're getting 5 cents per. So per usually means times. So 5 times C and 10 cents per bottle, or 10 times B. A mom is 3 times as old as her son. So we're going to say that the mom is M, is equals 3 times, literally means times, as old as her son. So the mom is 3 times S. The width of a rectangle is half of its length. So the width is half of its length. Half, so of means times its length. So the width is half times L. You could also say that the length is twice the width. That's another way of phrasing that one. Jacob walks 2 kilometers less than. So you want to be careful on this one. 2 kilometers less than Nancy. So Jacob we're going to call J, and he is 2 less than Nancy. So he's Nancy minus 2, not 2 minus Nancy. So less than, lots of times when you say less than, just like we did up here with shorter than, less than, that is a subtraction, but it's subtracted after, not before. So J equals N minus 2. Sam is 80% of the height of Jeff. So Sam is S, is equals 80% is 0.8. So Sam is 80% of, means times, and then the height of Jeff is going to be J. So Sam equals 0.8 of Jeff. A car is 2 feet. So a car is going to be C, is equals. 2 feet shorter than means something minus 2. A truck is going to go here. So the car is the truck minus 2 feet. A sister's age, so we're going to call that S for sister, is equals 6 years less than. We're going to put that at the back. So minus 6, the brother goes in front. So the sister is the brother minus 6. A school district has buses that carry 12 passengers and buses that carry 24 passengers. The total passenger capacity is 780. There are 20 more small buses than large buses. So we actually have a lot of information here. It's a bit of a hint that you see 2 blanks. So we're going to come up with 2 equations here. So we could say that the 780 is the total number of passengers. So that would be, we've got 2 kinds of buses. We've got small buses and we've got large buses. So that would be 12 people per small bus plus 24 people per large bus. We also know that there's 20 more small buses than large buses. So the number of small buses is the number of large buses plus 20. And when we come up with 2 equations that use the same 2 variables, we would actually call these together a system of equations. Because there's more than one. And they're referring to the same 2 variables, small and large buses. Okay, so the 2 linear equations that modeled the last example with the buses were 12s plus 24l equals 780 and s equals l plus 20. So a little bit of fill in the blanks here. A system of linear equations is formed by 2 or more linear equations that incorporate the same 2 variables. In this case, it was S and L. So they have to be the same 2 variables. And the solutions to the system is the pair of values that satisfies both equations. So for example, suppose you are told, so we're going to change it a little bit. Suppose you are told that there are 35 small buses and 15 large buses. Do these numbers satisfy both original equations? If so, then it is a solution to the problem. So they're telling us, hey, is it possible that there's 35 small buses and 15 large buses? Does that work? So that's kind of the question here. So what we're going to do is put it into both equations. So we're going to go back and check it up here. So I'm going to check. I'll call this one equation A and then that one equation B. I'm going to check my answer in equation A. So I'm going to put the 35 in the spot of the S and I'm going to put the 15 in the spot of the L. And see if that equals 780. So 12 times 35 is 420. 24 times 15 is 360. The question is, does that equal 780? And in fact, I do get 780 equals 780. I'm running out of room here. I'm going to sneak in another check. I'm going to check B. So now I have to check, do those fit this equation, those numbers? So 35, is that equal to 15 plus 20? Well, I get 35 equals 35. So yes. So because it works in both equations, then it is the solution to the problem. So the answer is yes, it works for both. Okay, so let's take a look at example 1 using a diagram to model a situation. So we're going to create a linear system, which is 2 equations that model this situation. So it talks about the Nunavut flag. Let's go ahead and look that up. Oh, beautiful flag. Okay, so here is the Nunavut flag. Something like this will work just fine. I'm actually just going to snip this out real quick and we'll pop it into our assignment. So let's say, whoops, there it is. So it tells us that the perimeter is 16 feet and that the length is 2 feet longer than the width. So first of all, let's label length and width on here, so we know what we're talking about. So I'm going to call that the length and I'm going to call that side the width. So what they're saying in the first sentence is that the perimeter is 16 feet. So 16 feet is going to be equal to, so that's going all the way around. That's what perimeter means. So the perimeter would be a length plus a width plus a length plus a width. In other words, 2 lengths plus 2 widths. And it's also saying that the length is 2 feet longer than the width. So what we need to do is see if we can check Denise's answer here. So Denise says that the Nunavut flag is 5 feet long and 3 feet wide. Is she correct? So we're going to check that answer in both of our equations. So I'm going to call the first one equation A and the second one in equation B. So 5 feet long, that would mean that L is 5 and W being 3 feet would be 3. So let's check. Is it true that 16 equals 2 times 5 plus 2 times 3? So it works out for equation A. Let's check it in equation B. Is it true that 5 is equal to 2 plus 3? And I do get it working out in both. So yes, she is correct. And that is because her answer works for both equations. If it only worked for one, that means it's not the solution. If it works for neither, it's definitely not the solution. Let's take a look at a second example. Example 2, using a table to create a linear system to model a situation. So in Calgary, a school raised $195 by collecting 3,000 items for recycling. The school received 5 cents for each pop can and 20 for each large plastic bottle. I'm assuming they need 20 cents. Probably should have said that. A, create a linear system by creating a table to model the situation. And B, the school collected 2,700 pop cans and 300 plastic bottles. Use the linear system to verify these numbers. Okay, so we're going to make a little chart here. I'm going to try to draw this as neatly as I can. I'm going to use the little line function. So I'm going to make a chart that has 4 columns. And 3 rows. We're going to go cans, bottles, and then the total. So just a really quick table. So we're going to have what is the refund per item? What is the number of items? And then how much money was raised? So we're going to analyze that for cans, for bottles, and then the total. So the number of cans we would say is C, and the number of bottles we would say is B. The refund per can is 5 cents. The refund per bottle is 20 cents. Now, if we think about that in terms of money, we should probably put it in decimal form because we know that the total raised was $195. So 5 cents and 20 cents. So I can't use 5 and 20 because that means I'm working in pennies. I want to work in dollars. So it's 0.05 and 0.2. So the amount of money raised would have been 0.05 times C for the cans, and for the bottles, it would have been 0.20 times B. I also know that the total number of cans and bottles was 3,000. Okay, so where are my equations? If I look at this table, there's actually one equation from this information, and then there's another equation from this information. I'll do them two different colors. So when I write them out, you can see the difference. Okay, so the first one, I'm going to call equation A is in that column, and then equation B. So equation A is actually that C plus B is equal to 3,000 for the total. So that was my yellow information. And a really small highlighter. Okay. For the green information, equation B, it's 0.05C plus 0.20B is equal to $195. So there are my two equations. So that is part A. That was all part A of the question. Part B of the question is asking, the school collected 2,700 pop cans and 300 plastic bottles. Use the linear system to verify these numbers. So let's make sure that works for both of our equations. Let's make this a little bit bigger. There we go. So I'm going to check those numbers in equation A. So 27 pop cans would have been the C, and the 300 plastic bottles would have been the B. And the question is, does that equal 3,000? And 2,700 plus 300 does equal 3,000. So it satisfies equation A. Now let's check it in B. If I put the 0.05 times 2,700, so 5 cents times 2,700 plus 20 cents times 300, does that equal $195? So I get $135 from my cans, and I get $60 from my bottles, and altogether that does equal $195. So yes, those are the right numbers because they verify both equations. I think that's the end of our notes for this section. Yeah, great. So that brings us to the end of section 7.1. And in our next section, as you can see with 7.2, we'll be solving them graphically. And then later on in the unit, we'll be solving them algebraically using two different methods. So today was more about what is a system of equations, how can we come up with some of them, and how can we check them to make sure that our answers or guesses are correct. Okay, thanks for tuning in, and we will catch you next time. Have a great day.